Welcome to part 2 of the series, Who Lives Where? In part 1, we took a look at functions, discussed some of their properties, and talked about where the range of a function lives. In this video, we want to focus on functions which satisfy some additional properties, which are required because the sets that they act on also have additional properties. I'm talking about vector spaces and linear transformations on them. So, what are linear transformations? Suppose V and W are vector spaces over the set of real numbers. So these are basically sets with a linear structure on them. Then a function is said to be a linear transformation if f is, then a function f from V to W is said to be a linear transformation if f satisfies the following properties. F respects addition, f respects addition, which is to say that f of v1 plus v2 is same as f of v1 plus f respects addition, which is to say that f of v1 plus v2 is same as f of v1 plus f of v2, and f respects scalar multiplication, which is saying that f times alpha v is same as alpha times f of v for any scalar alpha and for any vector v. F of v1 plus v2 is f of v1 plus f of v2 for any two vectors v1 and v2 in V, and f of alpha v is same as alpha times f of v for every alpha in R and v in V. What does this mean? If f from V to W is a linear transformation, then f is a function that satisfies the following two properties, which amounts to saying that f respects the linear structure on V and W. So let's read out these two properties. The first one says that f of v1 plus v2 is same as f of v1 plus f of v2 for any two vectors v1 and v2 in V. And the second one says that f of alpha v is same as alpha times f of v for every scalar alpha and for every v in V. So these two properties amount to saying the following. Here we have a vector space V, and here we have a vector space W, and we have a function between these two vector spaces. V is a vector space, so there's an addition operation on V. For any two vectors v1 and v2, we have a vector that comes about by the addition of v1 and v2. Now suppose I apply f to each of these vectors. I get images f of v1, f of v2, and f of v1 plus v2. The property about respecting addition says that if I apply addition in W to f of v1 and f of v2, the result that I get is the same as I would get if I apply f to the sum of vectors v1 and v2. So this is the same as f of v1 plus f of v2. This is the meaning of saying that f respects addition. It doesn't matter whether you do addition first and then apply the function f, or whether you first apply the function f to these vectors and then add them up. the result should be the same. The same goes for scalar multiplication. Respecting scalar multiplication amounts to saying that if you take a vector v and apply f to it, and suppose you take v and multiply alpha to get alpha v, when you apply f to alpha v, you'll get f of alpha v. This is same as first applying f to v and then multiplying alpha to it. The point about respecting scalar multiplication is similar. If you have a vector v to which you apply f and get f of v, then it should not matter whether you first apply alpha to v, then it should not matter whether you first multiply the part about scalar multiplication reads similarly. If you have a vector v in v and suppose you multiply a scalar alpha to it, now you could apply f to v as well as alpha v to obtain the elements f of v and f of alpha v. On the other hand, you could also multiply the scalar alpha to f of v in w. We say that the operation of scalar multiplication is respected if these two result in the same element. F of alpha v equals alpha times f of v. Such a function is called a linear transformation. We are interested in linear transformations because our underlying sets now have a vector space structure. A vector space structure is all about linearity. So we want functions that respect that linearity. Only then they are worth looking. These two conditions can be combined to make one. These two conditions can also be combined into one condition that reads f of alpha v1 plus beta v2 equals alpha f of v1 plus beta f of v2 for all alpha beta scalars and vectors v1 and v2 in V. Now, a linear transformation maps 0 to 0 in V. This is easy to see because suppose I take some x in V. On the one hand, I know that x minus x is 0. Suppose I apply f to this. F being a linear transformation, this is same as saying f is being applied to 0. On the other hand, f being a linear transformation means this is f of x minus f of x. These two are the same vectors in W. So you have a 0 here. And so that gives us that f of 0 is 0. The next important property satisfied by linear transformations is that linearly independent vectors in V map to linearly independent vectors in W. What this means is that if we start with a set of vectors v1 up to vk in V, which are linearly independent, then they are images, that is the set of all f1 up to fvk will also be linearly independent. So a linear transformation takes linearly independent sets to linearly independent sets. Finally, A linear transformation takes linear combinations to linear combinations. So if I have a linear combination alpha 1 b1 dot 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 plus alpha k vk in V, and I apply a linear transformation f to it, then this looks like a linear combination of the FVIs. So these are some useful and handy properties of linear transformations, which we will use all the time. Moving on, let's talk about the range space. Remember we earlier talked about the image of a function, and I told you, and at that time I told you that the image is also called as the range set. Let's talk about the range space of f. Since f is a function, it has an image or a range set called the range of f. This, simply by the fact that f is a map from V to W, tells us that the range or image of W tells us that the image of f lives in W, the codomain. But now, since W is a vector space, and f is not merely a function but a linear transformation, the range of f is also endowed with some special properties. In fact, range of f is a vector space in itself. It's a subspace of V. In, in fact, range of f is a subspace of W, which means it is a vector space in itself. This is not difficult to show. Suppose you pick up two elements in range of f, say W1 and W2 belong to range of f. What this means is that W1 can be written as f of V1 for some V1 in V, and W2 can be written as f of V2 for some V2 in V. We would like to show that range of f is a subspace. So we would like to consider a linear combination, say alpha W1 plus beta W2, and see if this is contained in the range of f. Well, this is equal to alpha of FV1 plus beta FV2 by just substituting for W1 and W2. And by the linearity of f applied in the reverse, this is the same as f of alpha V1 plus beta V2. And so we have written the term alpha W1 plus beta W2 as f applied to alpha V1 plus beta V2. This implies that alpha W1 plus beta W2 also belongs to the range of f. Thus, range of f is a subspace. There are two properties of the range of a linear transformation. There are two properties of a range of a linear transformation that we are going to require. So we'll look at them right here. One of those properties follows from what we just saw about properties of linear transformations. That linear transformations take linearly independent sets to linearly independent sets. So if f maps a vector space V to W, and the range of f falls in here, then the basis of V, which is a linearly independent set in V, gets mapped into the range of F. And these elements will stay, the images of these elements will stay linearly independent inside the range of F. If F is a linear transformation from V to W, then the basis of V, which is a linearly independent set of vectors in V, gets mapped into the range. And so the images of those elements are also going to be linearly independent inside the range. So F maps the basis of V to a linearly independent set inside the range of F, which in fact forms the basis of the range of F. To a basis of range of F. So this is a pretty important property that we will refer to from time to time. The other important property that I would like to mention, and this is also something we have already seen in the language of functions, that range of F is equal to W if and only if F is a surjective function. The other property that I would like to just mention here, but it follows from what we discussed about functions, is that F is surjective if and only if the range of F is actually equal to all of W. That follows simply from the definition of a surjective function, but it's worth a mention, so we put it down. Moving on, I would like to introduce you to the kernel of a function. A small disclaimer here that we don't immediately require this concept in the things that we are doing currently, but it will come up at some point. And also, some people in the group specifically asked about it, so here we go. But also some of the people in the group specifically asked about it. Moreover, if you are reading other material or looking at other content, people might mention this because it is a pretty important subspace. So then let's talk about it and understand what the null space of a linear transformation is. Next, I would like to introduce the kernel of a function, which is also known as the null space of a function. It is worth understanding this once, because even if we are not using it currently, a lot of content uses it. A lot of notes you see might be using this. Let me introduce now the kernel of a function, which is also known as the null space of a function. The definition is quite straightforward. The kernel of a function is the set of those elements in V that F sends to 0. Where does this live? Well, F is a function from V to W. The kernel F lives inside V. And F sends all of this to 0 in W. Okay. The kernel is also a subspace. Is a subspace in V. This is easy to show. If I have V1, V2 in kernel F, then I know that f of V1 equals f of V2 equals 0. This is by the definition. So consider the linear combination of V1 and V2, alpha V1 plus beta V2. What happens if I apply f to this element? F of alpha V1 plus beta V2 equals alpha f of V1 plus beta f of V2, which is alpha times 0 plus beta times 0 is 0. This implies alpha V1 plus beta V2 also belongs to kernel F. It's that simple. So kernel F is a subspace that lives inside V. Remember, range lives inside W. Let's look at some very simple examples. We'll do some simple examples. But before that, let's look at an important property that makes kernels very useful. The kernel of a function is singleton zero if and only if f is an injective function. Let's quickly go through the proof. Suppose f is injective. Then what this means is that suppose f is injective and suppose the kernel of f contains an element v. Definitely the kernel of f also contains 0 because, as we saw earlier, a linear transformation sends 0 to 0. So if v is in kernel of f, then f of v is equal to 0, which is f of 0. But f is injective. This implies v must be 0. Conversely, suppose f is injective, and if v is an element in kernel f, then f of v equals 0. But 0 also equals f of 0, since f is a linear transformation. Now the injectivity of f forces v to be 0. So what we have shown is that if I take any element in kernel f, it must be 0. So the kernel f contains only the 0 element. Conversely, if kernel of f contains only the singleton Conversely, if kernel f contains only the 0 element, and if we have two elements v1 and v2 such that f of v1 is equal to f of v2, then if v1 minus f v2 is 0, implies f of v1 minus v2 is 0. This implies v1 minus v2 must be 0, since the only element that f can send to 0 is 0. That's what kernel f being singleton 0 tells us. So this implies v1 minus v2 is 0, which implies v1 equals v2. So we started by saying let f(v1) be equal to f of v2, and the definitions took us to the conclusion that v1 must be equal to v2. Hence proved. Moving on, let's look at a couple of examples. Let's look at the example f from R to R, f of x equal to 2x, which we checked is a function. In fact, it's an injective and surjective function, as we checked before. We can now quickly check that f is also a linear transformation. Linear transformation by checking whether f of alpha x1 plus beta x2 is same as alpha fx1 plus beta fx2. Well, if I apply f to alpha x1 plus beta x2, by definition, this should give me twice. The definition says that f of x is twice of whatever the argument is. So, get this, which I can rewrite as alpha times 2x1 plus beta times 2x2. See how the associativity of scalars comes handy? So this is same as alpha times f of x1 plus beta times f of x2. And we've shown that f is a linear transformation. Let's talk about the range of f. In this case, both v and w are the set of real numbers. So the range of f lives, nevertheless, the range of f lives in the codomain here. Okay. So the range of f, sorry, I should change the chalk color here. So the range of f equals the set of all fx where x is in the domain. If I simply follow the definition, this is the set of all 2x where x is in R. Now my question is range of f, makes me think, right? If I take any real number and multiply 2 with it, whatever falls, or whatever I get, falls in the range of f. So, is this just the set of all even integers? No, because x can be any real number. Okay, so maybe I'm thinking, is it possible that range of f is equal to all of R? How do I check this? It is clear to me that range of f is contained in R. All I need to check is whether the reverse is true. Does every real number fall in the range of f? How do I check that? Let me take any real number y. Can I find x in R such that y equals f of x? If that becomes true, I will have shown that y actually belongs to range of f. And that will show this containment. But is this true? Yes, because what I can do is, given a y, I can take x to be half of y. In that case, f of x is twice y by 2 and hence y. So what I've just shown you is that if we start with any real number y, then y actually can be written as f of some real number, which means y belongs to range of f. And so, in fact, the set of real numbers is contained in the range of f. These two together show me that R is indeed equal to the range of f. So f is a surjective function. We check this only by using the properties of a linear transformation. We check this now using the properties of a linear transformation. But if you remember, we had checked it from basic principles earlier also. Oh, God. As a final, One final check we can do is on the kernel. What does the kernel of f tell us in this situation? The kernel of f is the set of all those vectors in R such that f of x is equal to 0. Well, f of x is equal to 0 implies 2x is equal to 0 because that's the definition of fx. But 2x would be 0 if and only if x would be 0. So this means that the kernel of f must be only the 0 element. And this implies that f must be injective, which is something that we had checked earlier from first principles. Let's do another example. This is also a function that we have looked at earlier. F be the function from R2 to R2 defined by f of x comma y equals 2x comma x plus y. We can check that this is a linear transformation. Just for convenience, I'm going to start writing my elements of R2 as vectors. So I'm going to replace this by f of x y equals 2x x plus y. Why? Because it's convenient, it saves some space. And I'm used to thinking about vectors as columns. All right, so suppose I pick up two elements in R2. So x1, y1 and x2, y2. And I apply f to these and I add them up. What I would get is 2x1 x1 plus y1 plus 2x2 x2 plus y2, which adds up to 2 times. And now I can actually pull this out, x1 plus x2. And this one I can write as x1 plus y1 plus x2 plus y2. And now we can recognize this as f of x1 plus x2 y1 plus y2. So f of x1 plus x2 y1 plus y2 is f of x1 y1 plus f of x2 y2. So this satisfies the first property for linearity. The second property can be easily checked also. F of alpha x1 alpha y1 is equal to 2 alpha x1 plus alpha y1. This is same as alpha times 2x1 x1 plus y1, and this is same as alpha times f of x1. So the second property or the second requirement for a linear transformation also checks out. Now let's talk about the range of f. The range of f is the set of all vectors x, y. The range of f is the set of all vectors f of x, y, where x, y are vectors in R2. This is the definition of the range. That means this is the set of all vectors that can be written in the form 2x x plus y, where x, y is an R2. So the question now is, what are all such vectors? Like before, I'm wondering if this is every vector in R2 expressible in this manner? For that, I will have to check that if I'm given a random vector x prime, y prime, can I express it as 2x x plus y for some x and y? As you will guess, yes indeed. I can take x prime to be x by 2, and I take y prime to be y minus x prime, which is now, I take y prime to be y minus x by 2. If this was my x prime y prime, then f of x prime y prime, sorry, then f of if this was my x prime y prime, then it can indeed be written as f of x by 2 y minus x by 2. I can ask whether a random vector x prime y prime in R2 can be written as f of a vector xy. Well, f of xy looks like 2x x plus y. So can I find x and y so that x prime y prime can be written as 2x x plus y? Yes, indeed. X prime y prime can be found in this way. So I want x prime to be 2x. So let me take x to be x prime by 2. And I take y to be y prime minus x prime by 2. Now if I apply f to this xy, I will end up getting x prime y prime. So what I've just shown is that any vector in R2 can be written as f of another vector xy in R2. This shows me that f is in fact surjective. So range of f is equal to R2. Although this has been the case in both the examples that we looked at, this is not true in general. There's just been these two cases where the function has turned out to be surjective. Let's quickly take a look at the kernel of a function. Let's quickly take a look at the kernel of f. This is the set of all vectors xy for which f of xy is 0. So let's parse this condition. F of xy is 2x x plus y equal to the 0 vector. This implies x must be 0, and then that would imply y must be 0. So the condition that fxy is 0 implies that both x and y must be 0. So the only elements in the kernel of f, the only element in the kernel of f is the 0 vector. Therefore f is injective. So it's a very useful property to know that if the kernel is trivial or contains. So it's a very useful property to know that if the kernel contains only the 0 element, then f is an injective function. That avoids you the work of trying to prove this from scratch. Although in this particular situation, checking from scratch is not difficult at all. Suppose f of x1, y1 were to be f of x2, y2. That would imply 2x1, x1 plus y1 equals 2x2, x2 plus y2. Well, this is simple. And we are done. Nevertheless, the kernel property for injectivity is used for more complicated functions and therefore is very useful to me. The next thing I want to talk about is something that, the next thing I want to talk about is how every linear transformation can be written as a matrix with respect to a chosen basis for V and W. Remember, once you have chosen a basis, you get a linear. Remember, once you have chosen a basis, you get a matrix formulation. If you change the basis, the matrix formulation will change. However, in most practical applications, one goes with the standard bases for both V and W, and so this doesn't become an issue. So suppose dimension of V is n and dimension of W is n. And if we choose a basis V1 or V2 up to Vn for V, W1 up to Wm for W. Then the matrix of a linear transformation from V to W with respect to these bases is obtained as the matrix. The first column being T applied to the first basis vector of V. The second column, the matrix of the linear transformation T from V to W is obtained by writing the matrix whose first column is the column of coefficients when you express T of V1 in the basis B prime. I'll tell you in a moment what this means. The second column is the vector of coefficients that you get when you express T of V2 in the basis B prime, and so on, up to the last vector Bn. Each of these needs to be expressed in this basis, and then the coefficients written in a column. Let me do a simple example. Suppose we look at the same linear transformation that we were working with before, and suppose we have checked that T is a linear transformation. And now I'm working with the standard basis on both sides. So B equals B prime equals 1, 0, 0, 1. In this situation, the matrix of T, as I wrote earlier, would be the matrix containing T of 1, 0 expressed in the basis 1, 0. In the first column, T of 0, 1, T of 0, 1 expressed in the basis B prime, making up the second column. So let's read what this means. T of 1, 0 is, well, according to the definition of T, it is 2, 1. And I need to express this in terms of this basis. And I know what the coefficients will be, 2 and 1 respectively. It is these coefficients that make up the first column here. Okay, 2, 1. Well, the beauty of the standard basis is that these coefficients will exactly be these terms. Similarly, T of 0, 1, according to the definition of T, this is going to be 0, 1, and which is indeed 0 times 1, 0, plus 1 times 0, 1. So it is this column, and this is the matrix representation of T with respect to this basis chosen both for the domain and for the codomain. If you change this basis, then this transformation, if you change this basis, then this representation will change. We have talked about this a few times, that changing the matrix representation will make the matrix entries look different. However, there are some intrinsic properties that will still remain the same. All right, so all right. Now, if you were to do the same, say with another basis, suppose I were to take, for simplicity, I'll have the same basis for both domain and codomain here. And suppose my basis were to be 1, 1, 1 minus 1. Then my matrix with respect to this basis would be T of 1, 1 expressed in this basis as the first column, and T of 1 minus 1 expressed in this basis as the second column. Well, let's find out what these are. Well, T of 1, 1 is 2, 2, and I can write this as with what coefficients? Well, if I put 1, 1, then that doesn't work. However, if I put half, half, oh, that doesn't work either. If I put 2, 0, that seems to be the correct coefficients. So the first column will contain 2, 0. Notice this is different from 2, 1 that I had earlier. Now if I apply t to 1 minus 1, the result is 2, 0, which I would get by using the coefficients 1, 1. And so my second column would be 1, 1. So the matrix representation of T in this new basis, let me call it B1, is different from the matrix representation of T in the basis B that we had earlier. These two matrices don't look the same. However, they will have the same determinant, they will have the same eigenvalues, and some more intrinsic properties remain the same. These two matrices will be similar. All right, moving on, we saw that every linear transformation has a matrix formulation. The converse is also true. Every matrix can be thought of as linear transformation. And this is a very important property. Given any m cross n matrix A, suppose I write the entries of the matrix as and now I think about matrix vector multiplication. And this results in the vector a11x1 plus a1nxn and so on. am1x1 to amnxn. This is a n cross 1 vector that results in an n cross 1 output. So this means that A takes a vector from Rn and produces a vector in Rm. We can check that A actually satisfies the properties required by a linear transformation, which means that A of x plus y is ax plus ay, and A of alpha x is alpha times ax. So you chess class? Huh? Huh? So the inside is already almost 6:30. Come on. इतना खायला देता चलो 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 ये almost falling down. Wow. अरे कसंच आहे कबुली हे काय ग काय कसंच आहे खाली पाणी पाणी आहे मी चॉकलेट मेल्ट करून घातलं खाऊन बघितलं स्वतः हो खाऊन बघितलं चांगलं ना हो खाऊन बघितलं पेन्सिल नाही पेन जा आता आल्यावर क्लासेस करतो पण मग उशीर होतो ना तिकडे क्लास सुरू झाला ना छोटं पाकिट आहे तोडली आहे कारण नाही असलं पोलीस बिलीस आणि आता चाव चाव पोळ्या करते आणि चाव चाव अरे इथे नको करू शकता ते मुलामुली हे कोणाचं तुला तुझं अरे पण आता सांगून उपयोग नाही तिकडे त्याचे देव टाकलेले आपल्याला नहीं नहीं, मी जस्ट घेऊन ठेवलं सांगितलं. माय गॉड, पंखे लावू नको जाईल तिकडे.
Are one of a kind. I don't know any other camp company in India currently catering to these, kind of students who are very good in math and age. I came first here because Vinay and I invited you to the United States. That's what I would say. I got it. Oh, that's good to see you. Fine. For me, that's right. I'm leaving in the moment. So yeah, it has been quite. So that some menu you can allow people to have because they still have on top of that. When I path around that. Older than this, they have the vocabulary, but because I realized, oh, I should be not have to be like that. Like I've never thought anyway. So all I can say, so we should trust our children. They are more resilient than we think. So that would be my advice to parents. Trust your children, they will be. So there is no question in my mind. So now, leave me time for a very long.
आहे इकडे. हो बस आहेत ना दुपारच्या.